So originally the title that I put in the abstract was something much more of a mouthful, but I wanted to give a more general presentation because I wanted to tell a sort of story of non-resonant and resonant processes occurring in the same types of samples, which are these guys, so thiophene and organic polymers derived from thiophene. And I will begin with a brief outline. So first with the systems that I studied, followed by the experimental setup, and then with the first project, which concerns these, one of these non-resonant processes. And then we move on to the resonant region, and I will talk about this X-ray induced charge transfer in polymers by corpuscle clock spectroscopy. So the systems that we studied, we have thiophene, which we studied in the gas phase, but as you can see here, it comes as a liquid. So what we had to do, we just do a few cycles of freeze-thaw pump, and the vapor that you generate in the gas phase, it's introduced slowly into the via a microleak valve, slowly into the chamber, and then we measure it. So if we take this guy and then we polymerize it, we obtain polythiophene. It's a really nice purple-looking powder. The only problem is that it's poorly conductive. So to tackle this, we mix it in approximately equal amounts with graphite, and by doing this, we tackle space charge. You can also see that we put some carbon tape just for extra measure. And then we have this guy here, P3HT, and if you take polythiophene and you stick a 6-carbon tail on carbon number 3, you obtain this polymer, and it was prepared as a thin film. So, and why these types of samples? Well, they're relevant in optoelectronics and the photovoltaics, for example, solar cells, the screens on your smartphones, and charge transport, and in general electron behavior. It's key for efficiency. So, we took all our samples. We went to the Soleil synchrotron in the outskirts of Paris, and we went to the galaxy's beamline, specifically to the Higgs end station. And here you can do gas phase, liquid phase, and solid state experiments. And why did we use Higgs? Not the end station, but rather the technique. So hard X-ray photoemission spectroscopy, because hard X-rays give you the element and site specificity, as well as high kinetic energy electrons that you need if you want to probe bulk properties of your systems. And now the first project. So this is called post-collision interaction from the gas phase to the solid state. So before I can explain what this post-collision interaction from now on PCI is, I want to introduce the subject of Auger decay, specifically KLL Auger decay. So in really simple terms, you have a system, a sulfur-containing system. You shoot X-rays and you eject a photoelectron. Now you create a vacancy here. And the system is unstable and is going to relax, and it's going to do so by filling this vacancy with an electron from an outer lying shell, which comes from the 2p orbital or the L shell. Now this excess energy, which is taken up by the system, is going to be released in the form of a rather energetic electron, also from the L shell. There we have the KLL or decay process. And now this PCI mechanism, what is it? So this is your sulfur-containing target. You shoot X-rays. Now you eject a relatively slow photoelectron, and this photoelectron, at first, it's going to experience a charge of +1, but as soon as Auger decay takes place, and as soon as it's being overtaken by the much faster Auger electron, it's going to experience a charge change from +1 to +2, and it's going to decelerate. So the Auger electron is going to do the opposite thing, and it's going to accelerate. Now, the short lifetime of this guy, which is about 1 femtosecond, coupled to the high kinetic energy of this guy, will translate into a strong three-body interaction between the residual ion, the photoelectron, and the Auger electron. And this will lead to PCI. And how is this PCI thing manifested? In Auger spectra, it will do so as a blue shift and distortion of the Auger lines. Here we have an example on argon, where we have a relatively, let's say, fastish photoelectron, and you can see that the line shape is, let's say, almost symmetrical. But when you have a really slow photoelectron, 1 electron volt, it's blue shifted by about 0.8 electron volt, and it's also quite distorted. And the motivation is quite basic. So many studies have been done in the gas phase in atoms and molecules, for example, OCS, CO, HBr, argon. In the condensed matter case, this is relatively scarce, and thus understanding PCI is of practical interest in that, for example, Auger electron spectroscopy, it's widely used in material science, where they characterize many interfaces and surfaces of a vast array of materials, and anything that may alter your energy distribution has to be carefully and properly described. So after we went to Soleil, we analyzed our data, and then we produced this colorful 2D maps where we have the Auger kinetic energy as a function of the incident photon energy and the intensity. And these features of interest here are the transitions to final state, the singlet 1s and the singlet 1d. We will focus on the much stronger one, singlet 1d. We also have this horizontal red line, which for the case of thiophene corresponds to the ionization potential, so the IP from now on. On the case of the solid, it's not as trivial, and this is what we call in this paper reference energy, namely to make the measurements share a common ground. So if you hop onto this blue line and you get closer and closer to the red line, you will see how Auger lines begin to blue shift and distort. So if you take slices at several different photon energies, as we have here, you will see how the PCI effect affects all of our samples. And if you have a really fast photoelectron, then you can estimate the magnitude of this PCI effect by obtaining these Auger spectra, which are not affected by PCI at all. But on the other hand, if you have a really slow photoelectron, say 1 electron volt or 3 electron volt, all of the lines will shift by about 0.8 electron volt, and in the case of thiophene, you will observe a really strong distortion. Not only that, we will have a preview of the line evolution, which is not the same for the case of the solids compared to the gas phase. So if we take all of our Auger spectra and we fit them, which were many, then we can have a direct comparison of the line energy shift, this delta E, as a function of the excess photon energy with respect to the IP, this E0 here. And for the case of the solids, blue P3HT and green polythiophene, we will see how they both decay to this zero shift line where we have no PCI, much slower compared to the case of the thiophene molecule. And also PCI is much stronger in the case of the solid state. But how do we interpret this? Well, for the solid state case, we need to take into account two main contributions, one which is electron scattering, and the second one is dielectric screening. And to do this, we collaborated with theoreticians Sergei Scheiderman and Leonid Gerchikov, who have vast experience with the PCI effect, and they have applied the iconal approximation to estimate this delta E guy in both cases, in the gas phase and the solid state. And this iconal approximation says that for the gas phase molecule, delta E, so the Auger energy line shift, is going to be given by the natural lifetime broadening, which is about 0.59 electron volt for sulfur, by the electric charge, and by the photoelectron and the Auger electron velocities. And this guy here is to, let's say, to take into account the interaction between the two outgoing electrons. But on the other hand, if you want to apply this iconal approximation to the solid state case, we need to take into account these two contributions. In the first one, scattering processes, your photoelectron has a probability of losing kinetic energy upon each encounter with anything that it meets. So this is inelastic scattering. On the other hand, your photoelectron is going to have its path travel drastically reduced by the time Auger decay takes place. And this is elastic scattering. And both of these will tend to an amplification of the PCI effect because they are, let's say, stealing energy from the photoelectron and giving it to the Auger electron. And we account for these scattering processes by incorporating this parameter gamma d, the damping width, to this guy here next to the lifetime broadening. And this gamma d is the photoelectron velocity normalized by the electron effective attenuation length. Now, on the other hand, dielectric screening, the Coulomb interaction between the outgoing photoelectron and the outgoing Auger electron is going to be efficiently screened because now the sulfur atom is embedded in a polymeric dielectric environment, and this is going to, like I said, efficiently screen the interaction, and this will tend to a decrease of the PCI effect. So this blue shift and distortion of the Auger lines is going to be determined by the interplay of these two guys here, and I will show you now how the experiment is compared against the theory, and we will see that it's a rather satisfactory agreement. And this says that in these types of samples, the PCI effect, as I said, the blue shift and distortion is going to be given by the interplay of scattering contributions and dielectric screening. So, namely, polarization screening will tend to a decrease of the PCI effect, and on the other hand, scattering effects will tend to amplify the PCI effect observed. And in these types of samples, PCI will be determined by the more dominant scattering effects. They will overtake whatever diminishing effects polarization screening may present. And one potential use of this is that given the right conditions, and if you have a liquid sample, you could extract the mean free path of an electron in water. And if you believe me, then PCI is a general effect, and PCI is everywhere. And now we move on to a resonant process, which happens below the IP. So X-ray induced charge transfer in polymers by Korhol-Klok spectroscopy. So Korhol-Klok spectroscopy, as the name implies, allows you to have a look at whatever processes may be occurring in your target within the time window given by the Korhol lifetime. In the case of sulfur, as I mentioned, it's about 1 femtosecond. And this is only possible if we are working under Raman conditions, namely a linear dispersion of the Auger kinetic energy as a function of the incident photon energy. And if we have a photon bandwidth that is narrower than the lifetime broadening, which will lead to the narrowing of the red spectator or resonant Auger peaks. Now, here we have a schematic of some resonant excitation and decay events. This one I have presented. So namely, you shoot X-rays, you eject a photoelectron. Now your system wants to undergo relaxation, and it does so by emission of a normal Auger electron. This normal Auger electron happens above the IP, so it's a non-resonant process. The characteristic of this is that this line here will have a constant kinetic energy as a function of the incident photon energy. Namely, if you look at a 2D map, the ones that I presented before, it looks like a line. And this guy here will lead to a two-hole final state. Now, if taking advantage of the capabilities of a synchrotron, namely that you can core-excite an electron from a core orbital and promote it to an unoccupied molecular orbital, you will put this electron in this orbital, and we will call it spectator electron. Now, the system, in this case, may decay in two ways. The first one will be resonant Auger decay. And we will emit a resonant Auger electron, and this electron is going to be blue shifted because of the screening action of the spectator electron. And secondly, because we are operating under Raman conditions, the kinetic energy is going to disperse linearly as a function of the incident photon energy. if you look at 2D map, the line is going to be diagonal. Now, I should state also that for the purposes of this talk, I am completely ignoring participator or decay. So, what happens now if this spectator electron finds a more favorable environment, let's say greener pastures, and it moves somewhere? Now, the system is going to decay in the same way as in the normal object case, and we will have a two-hole state. But this is going to be happening below the IP, meaning it's a resonant process. And this will provide us with a tool to identify charge transfer happening in the resonant region. And why? Because charge transfer, the CT channel, will be manifested as a peak to the lower kinetic energy side of the resonant channels. So this is CT, and these are the resonant Raman channels. And also these are blue shifted. So if you look at your 2D map, you will clearly see a straight line similar to this one, but happening below the ionization potential. So the samples I have already introduced. So polythiophene, which is a disorganized sample, and P3HT. P3HT as a thin film is quite ordered. The important thing here is that in the case of polythiophene, the electron may delocalize only along the polymer chain. On the other hand, because P3HT, in this case, we have imparted order to our sample, the electron may not only do this, it may jump between chains. So the mechanisms are the interchain mechanism for the case of the powder, and for the case of the thin film, it may be interchain or intrachain. We took these samples and went to Soleil, to the same end station, and we measured them. So the motivation. In 2008, a Japanese group measured polythiophene powder as using resonatory spectroscopy, and if you remember, CT channel is manifested as a peak to the lower kinetic energy side of the resonant channels. And here they found nothing, and granted this may have been affected by the resolution or sample preparation problems. In 2013, a Brazilian group studied polythiophene as a thin film using also resonatory spectroscopy, and they indeed find evidence of this guy here to the lower kinetic energy side. So, and their conclusion was that since now we have an ordered sample and the Japanese group did not see anything when the sample was disordered, then the electron by definition has to be preferring the interchain mechanism. So the disparity between these results prompt us to try to find an answer to this very simple question. What is the charge transfer mechanism in these types of samples? And also more generally, and I would say more importantly, because electron dynamics are relevant in optoelectronics, as I said, used in solar cells. These types of samples are used in solar cells, in screens, in big TVs, and so on. So after we went to Soleil, we plot our colorful 2D maps, and we have again the object kinetic energy, the incident photon energy. Some features of interest here. These are transitions to the final states, so the singlet 1s and singlet 1d, and this intense blob here is a excitation to the sigma star resonance, and this smaller blob is the excitation to the pi star resonance. And here we have the power, the disordered sample, and here we have the much ordered sample. These diagonal lines are to highlight the dispersive behavior of the OJ lines, meaning that we are indeed under Raman conditions. And now I want you to direct your eyes to this stadium purple shape here, and you are seeing here intensity to the lower kinetic energy side of the resonant Raman channel. So what you are seeing here is charge transfer taking place in both samples. So this is already new results, because we are seeing what the Japanese group didn't, and we are seeing also what the Brazilian group did not conclude. So These four plots here are the convolution of the spectra at these photon energies, which are the resonant photon energies of the pi star and the sigma star resonances. On the top, we have the powder. On the bottom, we have the film. On the left, we have the maximum or the resonant photon energy of the sigma star resonance. And in this case, we have in pink the sigma star resonance. On the purple case here, we have the pi star resonance, and here we have the CT channel. And this we attributed, as I said, to charge transfer. On the other hand, if you go to photon energies where the pi star resonance reaches a maximum, the peak is no longer green. And this is because we could not attribute it to CT. Instead, we have assigned it tentatively to a shake-up from an occupied band to an unoccupied molecular orbital occurring during OJ decay, as has been observed for the case of argon. And now, one reason we could not attribute it to charge transfer is because, as I mentioned at the beginning of this part, that the CT channel is going to have the same final state as normal OJ decay, a two-hole final state, meaning that it will be characterized by a constant kinetic energy which is not dependent on the incident photon energy. And as you can see here, as of photon energies around the maximum intensity of the sigma star resonance, the kinetic energy is constant. But if you go down in photon energy towards these photon energies, it begins to disperse. So this is namely the main reason why we could not call it charge transfer. You can also see the dispersive behavior of the Raman channels. So this is the sigma and the pi star, and they both behave as they should. But if you still do not believe me, which I hope that I do, believe me, we collaborated with smart people from Switzerland, so Marcella Iannuzzi and Fernanda Nunes, and also from Sweden, Mikael Odelius and Chinatami Kamal, and they have used real-time propagation, time-dependent density functional theory, which in our case allows us to have a peak at the electron density redistribution within the time window given by the core lifetime. And basically, with this Bader charge analysis, we can say that upon excitation of one ring here, electron density is going to be redistributed to the rings which are along the polymer chain, and there is a negligible amount of electron density being redistributed towards the rings above and below. So this is no CT, and this is we have CT. So the main conclusion is that in P3HT, in your order sample, we have indeed observed electron delocalization, or CT, along the polymeric chain. So to conclude, we observed CT in both powders and thin films. CT occurs upon sigma star excitation. It does not occur upon pi star excitation. Theoretical methods allowed us to confirm the dominant intra-chain mechanism along the polymer chain, and CT occurs in the low femtosecond regime. So as a reminder, in the first project, in the PCI case, screening reduces PCI and scattering increases PCI by, let's say, the photoelectron loses energy and it gives it to the other electron, and this will be reflected as a bullshift and distortion of the ray lines. And in the last case, in electron delocalization, we saw CT in both cases. This is new results, and theoretical methods confirm a dominant intrachain mechanism. Right. And I would like to thank all of these people, of course, but more importantly, my PhD supervisor. So this work was done during my PhD at Sorbonne University in France. And Tatiana Marchenko was my PhD supervisor. We were in the lab, in the group of Max Planck. And we'd like to also acknowledge funding from this Marie Curie network. And now I am a postdoc here in the group of Bernd Winter, the liquid jet photoelectron spectroscopy. And we are also in the same department where Gerard is the director. And thank you for your attention.
Thank you, Nicolas. Is there any questions?
Hi, super interesting talk. Thank you. I'm sorry to be asking the theory question, but do you know what functionals that they use for the TDDFT? Because the TDDFT usually is a bit suspicious for charge transfer states.
So I cannot remember the specifics of the function in this case, but since we were anticipating that the referees might ask these questions, Fernanda performed TDDFT and LMFS dynamics, and basically they both showed the same thing, that the electron is indeed moving along and it does not do so between chains.
Any other questions? No? Okay, so thank you again, Nicolas. We go to the next speaker.